Welcome to the solutions to the Regents Physics Momentum problem set, problems numbers 11 through 13. Let's go ahead and get started with 11. Two trucks that appear to be identical collide on an icy road. One was originally at rest. The trucks stick together and move off at more than half the original speed of the moving truck. What can you conclude about the contents of the two trucks? If we start with a before and after diagram, showing the situation that we have here. We have one truck of mass M. They appear to be identical. Another truck with the same mass M on a collision course. This truck is at rest. This truck has initial velocity VI to the left. Afterwards, these trucks are stuck together, so they have a combined mass of 2m. And this wants to know, this says that the final velocity is more than half the original speed of the moving truck. But what we're going to do in our scenario is find what the final velocity should be so that we can try and answer the question here. We start with our conservation of momentum statement, P before equals P after. What objects, if any, have momentum before the collision? It would be only this truck of mass M times its initial velocity VI. What objects, if any, have momentum after the collision? It would be the combined mass of the two trucks, 2m, moving at final velocity VF. So we have mvi equals 2m times VF. Notice the mass cancels in this equation. There's m in both terms. And so VI would be 2VF. Therefore, VF would be VI over 2. Now, this is what the final velocity of the two trucks after should be. This says that it moves off at more than half the original speed of the moving truck. What this indicates is, though they appear identical, that the original moving truck must have more mass, either more occupants or something in its payload here, to give it more mass than what appears to be the identical mass M of this truck. So this truck must have more mass than what it appears to in order for the initial velocity, for the final velocity to be more than half the original speed. Okay, so this M value must be greater than what it appears. All right, let's move on to number 12. A 0.115 kilogram hockey puck moving at 35 meters per second strikes a 0.265 kilogram octopus thrown onto the ice by an overzealous Red Wings fan. The puck and the octopus stick together and slide off together. Draw a before and after diagram of this situation. What is the velocity of the puck-octopus combination after the collision? This may seem like a very contrived scenario here to you, but I assure you this is 100% accurate. That yes, these nutcase Red Wings fans do throw out octopi on the ice after a goal is scored. It's a tradition there in the Detroit on the Detroit home ice. So, as requested, we start with the before and after diagram. We have the 35 meter per second 0.115 kilogram puck moving to the right, a 0.265 kilogram octopus sitting on the ice with no velocity. After collision, the two stick together, and the combined mass of 0.380 kilograms moves off at a final velocity we are asked to find. To solve this problem, once we set up our before and after diagram, we start with our conservation of momentum statement, P before equals P after. What objects, if any, have momentum beforehand? Just the puck. So this would be 0.115 kilograms times 35 meters per second. What objects, if any, have momentum after the collision? They both do combined, so we add their mass together and are solving for the final velocity VF. We do the algebra and the math. Pause this video if you need a moment to do that. And we get a final velocity of 10.6 meters per second. And finally, number 13, a 0.2 kilogram plastic ball moves with a velocity of 0.3 meters per second. It collides with a second plastic ball of mass 0.1 kilogram, which is moving along the same line at a speed of 0.1 meter per second. After the collision, both balls continue moving separately in the same original direction. The speed of the 0.1 kilogram ball after collision is 0.26 meters per second. To draw a before and after diagram of this situation, and what's the new velocity of the 0.2 kilogram ball after collision? All right, so we start with a before and after diagram. What objects, if any, have momentum beforehand? And the answer to that is both, and they are separate. So we have our 0.2 moving at 0.3, our 0.1 moving at 0.1 meters per second in the same direction. Okay, so these two are moving in the same direction. This one moves faster than this one, catches up to it, hits it, and after we have our 0.2 kilogram that we're trying to find the final velocity of, and we're told that our 0.1 kilogram continues at 0.260 meters per second. Now you may ask, how do we know whether the final velocity is traveling to the right or to the left of this ball? Could it hit and then bounce back? The answer to that is yes, but what we're going to do is we're going to solve for the final velocity and let the sign of our answer tell us the direction that the final velocity is headed. So naturally, of course, next we set up our P before equals P after conservation of momentum statement. What objects, if any, have momentum before? The answer is both and separate. So we have to have separate momentum statements for each object. 0.2 times 0.3 plus 0.1 times 0.1. What objects, if any, have momentum after? Answer once again is both, and once again is separate. So we have to have separate momentum statements for each object after collision as well, and add them together. We know our 0.1 is going 0.260 meters per second, and our 0.2 kilogram object is what we're trying to find the final velocity for. Kilograms should be substituted here. We go ahead and do the math. We would multiply this. We would add the product of this. We would subtract the product of this and then divide by 0.2. Solve for VF. Pause if you need a moment to do so. And we get 0.220 meters per second. Notice the sign of this VF is a positive value, and what that tells us is that this object is moving to the right after collision, just like the original velocities and final velocity of the 0.1 also are. That'll do it on problems 11 through 13. More practice with conservation of momentum as we do number 14 together in class tomorrow.